Alrighty then, we're going to use powers of 10 to estimate quantities. So either really big numbers or really little numbers. We're going to use powers of 10 to estimate those numbers. This serves as kind of an introduction to the last two lessons of the chapter, which will be on scientific notation. And we really need to have a handle on powers of 10 for that to be successful later on. So powers of 10, it turns out, is really, really easy. Okay, by the way, that's why metric system is really so much easier than what we do. I know we don't like to admit it, but metric system really is easier because it's just all based on powers of 10. So like a kilometer is 1,000 meters, and that's easy to remember, right? So powers of 10 are really easy because like 10 to the 9th power is just a 1 with 9 zeros after it. 10 to the 23rd power would be a 1 with 23 zeros after it. All right, 10 to the 11th power, that would be a 1 with 11 zeros after it. I mean, it's super simple to use powers of 10 to estimate really big numbers. And we can do the same with really little numbers. 10 to the negative 10th power would be a 1 with 10 zeros in front of it. You got to count the 0 that's in front of the decimal place. So there'd be a 0, then a decimal, and then there'd be 9 more zeros, and then a 1. So that would be 10 to the negative 10th power. Okay, so it's super simple to think about powers of 10, and we're going to use those powers of 10 to estimate really big and really little numbers. You ready to go?
Yeah.
Okay, so this one, by the end of this lesson, we want to estimate large and small quantities using a power of 10. That's our goal today. All right, here we go. We're going to start off with a warm-up question with my friends. We good to go?
Yep.
Okay. I thought there was a question or something. People were talking. So Keegan and Jeff did some research and found out that there are 7 quintillion, 492 quadrillion grains of sand on Earth. I don't know where they researched this. I don't know what the basis of their fact checking is, but somebody has estimated that number to be 7 quintillion, 492 quadrillion grains of sand.
I don't know who would count that.
I think most of them were in my shoes the last time I went to the beach. All right. So Jeff says that it is about 7 times 10 to the 15th grains of sand. But Keegan says that it's really about 7 times 10 to the 18th grains of sand. How might Jeff have determined his estimate, and how might Keegan have determined his estimate? Any thoughts?
Huh? Oh. Well, Jeff. Yes.
So this is the real number that we're talking about.
10 times 10 is 100. So I'm thinking that if you count 2, 4, 6, 8, 10, it's 10 to the 10th power. I don't know how to count.
Okay, Remington, what do you think?
Just counted all the zeros.
Okay,
And you counted this, every number to the 7.
okay, so Jeff just counted the zeros, which means he just counted these guys right here. There's 15 zeros at the end of that number. But Keegan counted more than that. What? Anybody think of a term that tells us what Keegan counted? He counted every number. I'm looking for a term. Starts with the letter P.
Power.
It's two words. Starts
Powers
with P.
of powers.
Ends with
Exponent.
lace value.
Power, which, I don't know.
No power. Just starts with a P. Ends with lace value. Place value, very good. Okay, he counted the place values. All right, he counted the place values of all of the digits after the 7, right? How many place values come after the 7? 18 place values come after the 7. Jeff only counted the zeros. Who do we think is probably correct here?
Keegan.
Keegan counted all of the place values. He accounted for all of the numbers after the 7 by saying 10 to the 18th power. But Keegan, or Jeff, only accounted for these zeros. Well, if he only counts the zeros, then we left 3 place values out. Okay? And so 7 times 10 to the 15th power would be 7 quadrillion grains of sand. But 7 times 10 to the 18th power, that would be 7 quintillion grains of sand. There's a big difference between a quadrillion and a quintillion. Okay, those are numbers are so big we really can't even imagine them anyway. But there's 1,000 times difference, right? He's off by 1,000%. 1,000 times probably would be a better way to say that. So Jeff, nice try, Jeff, but Keegan got it right. And then if we go to this screen, whose estimate we like Keegan's estimate more because he accounts for all of the place values, not just the zeros. And then I think there's a question down. Whoops! What in the world? That's not what I wanted to do. There we go. Question down at the bottom. Do you think the two estimates are close in value? I kind of already gave that away too. No, one is Jeff is 1,000 times more than Keegan in his estimate, and 1,000 is kind of a big difference, right? If you agree to pay me for a job and you get it wrong by 1,000 times, so if you agree to pay me $1,000 to do a job and you're 1,000 times off, that means you're just offering me $1. I'm not gonna be real happy with that. So, yeah, there you go. All right, so that's a good warm up for today. I like that one. That kind of gets into what we're doing. So here we go. Next. Oh, look, a video.
I don't like your video.
This is a pretty good video. This one does a good job.
You say that about all the videos.
No, I don't. I've told you there's been several that where I'm like, I don't really like this video. It's not very good. Been a couple times.
When would you use a power of 10 to estimate a quantity?
Plug in my speaker. That's all right. It's gonna be hard to hear. Oops.
Think about this question during the lesson. Janelle is comparing the estimated populations of Japan and China. The estimated population of Japan is 126,818,019. Here's the estimated population of China.
Billion.
How can Janelle compare the two populations more easily? You can estimate large quantities and write them in a format that is easier to compare. Janelle knows the populations of China and Japan. Why might she want to estimate the population of a country?
Why are we gonna estimate instead of just using the actual number?
Because
Bryson.
Estimating is easier.
Okay, we can estimate it to a number that's easier to deal with, right? Rather than every time I want to say the population of China, if I have to say 1,402,941,487, I'm gonna get tired of saying that over and over. So using an estimate just makes it easier to deal with the numbers. That's one reason. Any other reasons, Mason?
the population's always growing.
It's always changing, all right? From the time that I said that number like 30 seconds ago to now, that number has changed. Like the actual population of China, it changes every second, right? Because somebody's being born, somebody's dying. Every second in China. So, and that's okay, that's the way it goes, but It's just changing, so we gotta estimate so that we can actually have a number we can work with.
The population is constantly changing, so it makes sense to work with an estimated quantity. To begin, estimate each population by rounding to the greatest place value. The population of China rounds to 1 billion, and Japan's population rounds to 100 million. How do you determine whether to round the initial place value up or down?
Ooh, this is a big one because sometimes we're not very good at rounding. Sometimes we kind of are we're not very accurate with our rounding sometimes, and rounding is a real thing that we need to do well. So so we've got to make sure we do it. How do we know, Mason?
Cause if it's below 5, go down, if it's above or 5, you go up.
All right, I learned something today in second hour when we said, somebody said, if the number is 4 or less, anybody know?
I digress.
Let it rest. If it's 5 or more, let it soar. I've never heard that before. I don't teach this lesson very much like rounding. You're supposed to know how to round before you get to my room anyway. So I just had never heard that. If it's 4 or less, let it rest. If it's 5 or more, let it soar. I like it. That helps me remember it. So in both of these cases, you look at the one's the number we want to look at, then we look at the one next to it, 4 or less, so it goes down to 1. And this one, 126 million, we round down to 100 million as well. Okay. Boop.
Look at the place value to the right of the initial place value. Round up if the number is 5 or greater. The initial number does not change if the number to the right of the initial place value is less than 5.
Okay.
Drag zeros to determine the power of 10 for each population. So what power of 10, we rounded the population of China to 1 billion. What power of 10 is that going to be? Danica.
9.
Yeah, it's 10 to the 9th power. Ah, goodness, okay. And we can do 1, 2, ooh, stop that. 3, 4, I don't know why they make us do this. 5, 6, 7, 8, 9. By the way, do you know you have access to all these resources? This whole thing that I'm doing online, you could actually do this whole thing step by step on your Chromebooks. So if this kind of thing appeals to you and you like dragging zeros to estimate powers of 10, you have access to this very same activity. Not while I'm doing it right now. I'm the one playing at the moment. Okay? So then, and you can even do this. Now on yours, you'd have to use your mouse and drag it that way. I get to use the touch screen. This is way awesomer. This one would be 10 to the what?
8.
8th power. How did you get the 9 and the 8, those of you that did that?
I counted.
Count the zeros
Oops, too many.
over.
Okay, sorry, I went too far. You count the place values, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. All we did is count. It's 10 to the 9th power. This one we count. 1, 2, 3, 4, 5, 6, 7, 8. It's 10 to the 8th power. It's just counting, guys.
Yeah, guys.
Counting, well, it tends to be pretty easy.
Janelle can write each number as a single digit times a power of 10. She can count the zeros to determine the power of 10. 1 billion has 9 zeros, so it can be expressed as 1 times 10 to the power of 9. There are 8 zeros in 100 million. 1 times 10 to the power of 8.
Thank you. Teach.
Janelle's second step is to compare the estimated values. Which symbol correctly completes the statement?
Select your answer.
So is 10 to the 9th less than, greater than, less than or equal, greater than equal to 10 to the 8th?
Greater than.
10 to the 9th is bigger than 10 to the 8th. It's kind of obvious because 1 billion is more than 100 million, right?
Yeah.
There you go.
10 to the power of 9 is greater than 10 to the power of 8. So, 1 times 10 to the power of 9 is greater than 1 times 10 to the power of 8. That's how Janelle can use estimates with powers of 10 to compare the populations more easily.
There you go. Nothing too super challenging, I feel like, in this first part of the lesson. So light travels at 299,792,458 meters per second, and sound travels at 332 meters per second. So we're going to use a power of 10 to compare the speed of light to the speed of sound. Guys, this is not that difficult.
3.
What number are we going to round? We're going to look at the biggest number. We're going to look at the number 2. And then the number next to it is 9. So it's 5 or more.
3,000.
Let it soar. So we're going to round it to the 300 million. All right. So how many zeros are in the rounded number?
8.
3, 6, 7, 8. There are 8 zeros. So the estimated speed of light is, all you have to do is take your first number of the rounded number and take that, how many zeros there are, times 10 to the 8th. 3 times 10 to the 8th is 300 million. So then let's round the next one. 322 rounded to the greatest place value is
300.
300. How many zeros?
2.
So it is 3 times 10 to the second power. Okay? So 3 times 10 to the second, 3 times 10 to the 8th is greater than 3 times 10 to the second. It really is that simple. That's pretty easy. That's all we want to do. So now, convince me that you know how to do this.
Country A has a population of 1,238,682,005.
That's different.
And country B has a population of 1,106,487,394. How would you compare these populations?
What do you notice if we're going to round both of these? What do you notice about it?
They go.
They're both
They-
equal to each
They're
other.
both 1.
It's going to look like they're equal if we round them both to the largest digit, to the largest place value. So what can we do to help ourselves out so that we can compare them?
Round it to the second one.
We can do it to the second digit. And so I have to write up here. For some reason, I can't write below this line. So if I go up here, I can round country A to 1,200,000,000. Right? So how would I change that into a power of 10? For these up here, I did the first digit and then counted the zeros. What can I look at here instead of just looking at the first digit? Can I look at the first 2 digits? Is that okay? Can I do 12 times 10 to the what? It's still going to be, then just count the zeros. So it's 12 times 10 to the 8th, and that's okay. I can still estimate a number that way. And then I can take country B, and I can do the first same thing. I can't write. There we go. 11, or it's 1,100,000,000. Okay, I'm right at the bottom where I can write. Okay, so that would be 11 times 10 to the 8th. So we can still compare numbers even if we have to go one more digit past that, right?
Yeah.
Did that make it like super way harder?
No.
Yeah.
Really doesn't. All right. That's as far down as I can go right there. All right. Okay. Now, you ready for what's next?
No?
Yes.
Maybe. maybe.
What if I need to round some really tiny numbers? Can I use powers of 10 to do that? Of course I can, okay? So, 0.000177763 meters is how thick a human hair is if we measure it using a laser beam. And a sheet of paper is about 0.0013 meters. So how do the two thicknesses compare? Well, we can, really? Again? Can I not? I used to be able to do this. I guess not. Is it on this screen? Oh, there it is. Maybe that's what I wanted to do, okay. So write the estimated thickness of a human hair using a single digit and a power of 10. So it's the same steps that we just did. We want to look at the first digit that's not a 0. Okay? I can see that first digit that's not a 0 right here. Okay? And so look at the next digit, that would be a 7. So since that's a 7, 5 or more, let it soar. So we're going to raise this one to 0.0002. So then I would still take this number, write that digit, and then count the zeros. 1, 2, 3, 4 zeros. You have to count the 1 in front of the decimal place. So 2 times 10 to the -4th. Why is it a -4 this time?
Because it's going back.
Because we're going backwards. We're making small numbers. And we talked about this last week. Negative exponents don't make negative numbers. They make tiny numbers. They make fractions. Okay? So then we do the same thing with this one. Find that first non-zero digit is a 1. The number next to it is a 3, so we're going to leave it as a 1. 0, 0, 0, 1. So put a 1, count the zeros. There's 3 of them. 1 times 10 to the -3rd. -3 is bigger than, or 10 to the -3 is bigger than 10 to the -4. We have to think about negative numbers being a little bit backwards, right?
They are back.
So a human hair is thinner than a sheet of paper because it's got a smaller exponent. -4 is a smaller exponent than -3.
Cool.
Okay? All right, so I think there's some practice ones for us to do on this. Oh, the gross domestic product. We're going to practice on this one.
I already wrote mine down.
Wait a minute.
So the gross domestic product of Canada is $1,785,000,000,000,000. The gross domestic product of the U.S. is 17,348,375,000,000,000. I got that right. $75 billion.
I thought we were that much in debt.
Oh, we are in debt.
Our debt's not quite that big. So let's see what they do. Write each gross domestic product as a single digit times the power of 10. So what do we do with Canada? Take that largest digit, the 7 rounds it up to 2, so it's 2 times 10 to the 15th. And then for the US, it's 2 times 10 to the 16th. So which one is bigger?
16.
16 is bigger than 15. Compare the two estimates.
That makes sense.
2 times 10 to the 16th is greater than 2 times 10 to the 15th.
No. No way.
And how much bigger is it?
It's about one.
It's about 10 times bigger. Well, I'd rather have 10 times more money than Canada. It's not a little. Alright, so this one, we've got to do something similar here. So this one, they want us to estimate the values and then see which one's bigger, but by how much is it bigger? This one's a little bit trickier than the last one, to be honest with you. You ready? Guys, lots of talking going on. If you need to move away from people who are talking to you, do it now so I don't have to move you. Alright. There are approximately 1,020,000,000 cars in the world. The number of cars in the US is approximately 239,800,000. So we are going to estimate. So for the cars in the world, we want to take that first digit, which is in the billions place. Are we rounding up or are we staying the same?
We're rounding.
So is it going up or is it staying the same? Staying the same, because the number next to it's a 0. So it's going to be 1 times 10 to the what?
Power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9. Count the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. I decided not to count.
All right, then we're going to look at the US. So here's our biggest digit. Are we going to round it up or are we going to keep it the same?
We're gonna round it. No, we're gonna keep it the same. Next number.
Number next to it is a 3, so it stays the same. So that's going to be 2 times 10 to the, count the place values after the 2. 1, 2, 3, 4, 5, 6, 7, 8. 2 times 10 to the 8. So, 1 times 10 to the 9th and 2 times 10 to the 8. Which one's bigger?
1 times 10 to the 9th.
10 to the 9th is bigger than 10 to the 8th. So that one's bigger, even though the 2 is bigger than the 1, that's not what we're looking at. We're looking at the powers of 10. So the 10 to the 9th is bigger than the 10 to the 8th. All right, but how much bigger is it?
It's pretty big. It's specifically 10 times bigger than it.
Okay, it would be 10 times bigger to go from 8 to 9. That's true, because we'd have to add a whole other place value. But we've got to account that there's a 2 and a 1 here. So it's really not 10 times bigger. It's how much? It's 5 times bigger. Okay, it's 5 times more cars in the world than there are in the US. Okay, the world has 5 times as many cars as the US. So that's pretty remarkable considering we've got about 5% of the Earth's population, isn't it? 5%?
That must be like,
But we've got 20% of the Earth's cars. Cars or people? China has the most people. And then India. In your lifetime, India will pass China as having the most people. That'll happen in the next probably 10 or 20 years.
What are there more of, wheels or doors?
How do you know
What?
it?
What are there more of, wheels or doors?
Wheels or doors?
Wheels.
That's an interesting question.
It would have to be.
I suppose doors, because there's lots of people that don't have cars that have houses with doors in them.
I'll think of it.
But
Have wheels.
Oh, yeah,
are we
what
talking
is-
now? Are we talking tractors and bicycles? And if we're talking those kind of wheels too, if we're including bicycles,
Semis,
probably
semi-trailers.
wheels.
No, but
Yeah.
what about like skyscrapers?
But cars have doors,
Yeah.
and skyscrapers have a lot of doors in them.
But
Yeah.
You make a good point.
elevators.
I don't know. That's an interesting question.
Think of elevators.
Where'd you do that? Did you just make that up?
No, I've heard that.
Oh, you've asked that. We've heard that question. Okay.
But
That's
think
an interesting
think of
question.
elevators.
Elevators, a door on every floor for elevators.
But no.
And they got 2 doors.
But think of the wheels.
Oh, the elevators have wheels that keep them on the tracks that got, oh man, you're making my brain hurt. All right. Okay, is that the last one? All right, so your assignment, hey, listen. Your assignment, pages 57 to 58, but I'm not here tomorrow, so when is it due? Wednesday is when this assignment is due, which means you will have, hey, I'm not done talking. You will have an in-class assignment tomorrow, some online stuff to do, but you'll also have class time tomorrow to work on this. So this, I would not do it as homework tonight, I would do it during class tomorrow. along with the in-class assignment that you'll have. So there'll be plenty to do during class time to keep you busy.
Just to finish,